Morning students, today we are going to see the topic Differential Geometry. I am DR.G.SUDHA, Assistant Professor of Mathematics, A.D.M College for Women, NAGAPATTINAM. First let us go for the topic tangent plane and surface normal. Let R vector equal to R vector of u of t, v of t be the general curve lying on the surface passing through the points u of t, v of t. Then the tangent to the curve at any point p on the surface is dr by dt is equal to dou r by dou u into du by dt plus dou r by dou v into dv by dt is equal to r1 into du by dt plus r2 into dv by dt. This is the tangent plane, that is the general curve. Tangent plane definition. Tangent to any curve drawn on the surface is called a tangent line to the surface. From the equation 1, that is dr by dt, the tangent dr by dt is a linear r1 vector and r2 vector. Since r1 cross r2 is not equal to 0, r1 and r2 are non-zero and independent to the tangent to different curves through p on the surface lie in a plane containing independent vectors r1 and r2 at p. This plane is called the tangent plane at p. Next, the definition, surface normal. The normal to the surface at p is a line through p and perpendicular to the tangent at p. Since r1 and r2 lie in the tangent plane at p and passing through the point p, the normal is perpendicular to both r1 and r2 and it is parallel to r1 cross r2. The normal at p is fixed by the following convention. If n vector denote the unit normal at p, then r1, r2 and n vector in this order should form a right-handed system. Using this convention, we have n vector is equal to r1 cross r2 divided by modulus of r1 cross r2. That is r1 cross r2 divided by h. That means where h is equal to modulus of r1 cross r2. Since r1 cross r2 is not equal to 0 and h is equal to modulus of r1 cross r2 is not equal to 0, which shows that it is always positive number. And nh is equal to modulus of r1 cross r2. We see the diagram, that is u is equal to constant and v is also constant. r1 vector and r2 are vectors and n is the unit normal. Next, let us go for the theorem. The equation of the normal n vector at p on the surface r vector is equal to r vector of uv is capital R is equal to r plus a into r1 cross r2. Proof. Let capital R vector be the position vector of any point on the normal to the surface p, whose vector is r vector equal to r vector of uv. Since r1 cross r2 gives the direction of the normal and the difference r capital R minus small r lies along the normal, r1 cross r2 and capital R minus small r are parallel. So that we have r minus r, the difference is equal to, the difference of r minus r is equal to a into r1 cross r2, where a is a parameter. Hence, capital R is equal to small r plus a into r1 cross r2 gives the equation of the normal at p. Next, let us go for the problem. Obtain the surface equation of the cone with a semi-vertical angle alpha and find the singularities. Parametric curve, tangent plane at a point and the surface normal. See the diagram. P of xy and m of xyz, p of xyz and m of xyz are the points and xyz are the axis, alpha is the angle. The proof, taking the axis of the curves on the z-axis, let p of xy be any point of the cone, draw pn and pm is perpendicular to the axis of the cone and xy plane referred in the diagram. Np is equal to u and v be the angle of rotation of the planes, so that angle xym is equal to v. Hence, x equal to u cos v, y is equal to u sin v and z is equal to cot alpha. Thus, the parametric representation of alpha point on the surface of the cone is r vector is equal to u cos v, u sin v and u cot alpha. R1 is equal to, R1 vector is cos v, that is differentiate with respect to u. R1 means that is differentiate r vector with respect to u, it is cos v and sin v cot alpha. R2 means differentiate r with respect to v, that is minus u sin v, u cos v, and there is no v in the z plane, so that is 0. Now r1 cross r2 is equal to at w is equal to 0. Hence the vertex of the cone is the only singularities. It is the essential singularities. When u is equal to constant, the distance p from the axis is u is equal to constant, so that p describe a circle. Hence the system of parametric curves when u is equal to constant is a system of parallel circles with the center of the z-axis. When v is equal to constant, make a constant angle with the x-axis so that the parametric curves are the intersection of this plane with the cone along the generator. Further, R1 cross R2 is equal to 0 so that the parametric curves are orthogonal. That is, R1 cross R2 is equal to determinant of ijk cos v sin v cot alpha, that is R1 vector values, and R2 vector values minus u sin v, u cos v 0. Expand the determinant value R1 cross R2, we get the value R1 cross R2 is equal to I vector. Expand row wise, we get I vector is into minus u cos v into cot alpha minus j vector into u sin v cot alpha plus k into u. That is usual determinant expansion. Hence the equation to the tangent plane at any point is, for the modulus of R1 cross R2 is equal to square root of u squared cos squared v into cot squared alpha plus u squared sin squared v into cot squared alpha plus u squared. Taking modulus value of modulus R1 cross R2, that we get the value answer is u cosecant alpha. Now capital N vector formula R1 cross R2 divided by modulus of R1 cross R2, already mentioned in the first slide. That is value is minus cos v into cos alpha minus sin v into cos alpha sin alpha. Next let us go for another theorem statement. A proper parametric transformation either leaves every normal unchanged or reverse the direction of the normal. The proof of the theorem: let R vector is equal to R vector of uv be the given surface, and let parametric transformation be u dash equal to phi of uv and v dash is equal to psi of uv. Since the parametric transformation is proper, that is j is equal to dou of u dash v dash divided by dou of uv is not equal to 0. Transformation is proper, that is j is not equal to 0. As in the case of 5 in the previous section, we have dou r squared by dou v dou u into dou r by dou v is equal to dou r by dou u squared into dou r by dou v squared into dou of u dash v dash divided by dou of uv. Using h dash and n dash in the above, we get hn is equal to h dash n dash into dou of u dash v dash divided by dou of uv. Since h dash were always positive, n and n dash are of the same sign if modulus of f is greater than 0 and are of the opposite sign. Since j is a continuous function of the parameter uv is the whole domain and j does not vanish in D. J retain the same sign in D. This proves that n and n dash have the same sign. Next let us go for the general surface of the revolution. Definition: surface of revolution, that is a surface generated by the rotation of a plane curve about an axis in its plane is called a surface of revolution. The theorem follows the surface of revolution. The positive vector of any point on the surface of revolution generated by the curve g of u, 0, f of u in the xyz plane is r is equal to g of u into cos v, g of v into sin v, f of u, where v is the angle of rotation about the z-axis. The proof of the above theorem: let us take the z-axis as the axis of rotation and let g of u, 0, f of u be the parametric representation of the general curve in the xyz plane. Let a be the point on the curve. Then its coordinates g of u gives the direction of a from the z-axis. When the curve revolves about the z-axis, a trace has put a circle with radius g of u when the plane through the z-axis has rotated through an angle gamma. Let p be the position of the point corresponding to a on the curve after rotation. Draw pm and pn perpendicular to xy and xyz planes. Then an is equal to pn, that is g of u, and om equal to pn. If xyz are the coordinates of p, then we have x coordinate is equal to om cos v, that is equal to pn into cos v, that is g of u cos v, and y coordinate is equal to om sin v, that is pn sin v, that is equal to g of u into sin v, and z coordinate is pm is equal to f of u. Hence the position vector of a point P on the surface is, R vector is G of u cos V, G of V sin V, F of u, where the domain UV lies between V lies between the value 0 and 2 pi with a suitable range for u which depends on the surface. Next we shall find the parametric curves. Let P be a point on the surface with u is equal to constant, so that G of u is also a constant. U constant means that G of u is also a constant. Then the locus of the points, like P is a circle with radius G of u for a complete rotation as xi arises from 0 to 2 pi. Thus the XOY plane, as in the case of sphere, we call them as parallel. Let V is equal to constant, since V gives the angle of the plane rotation in this position. The parametric curves or the curves of intersection of this plane of the rotation with the surface, we call these curves meridians. Further, R1 is equal to G dash cos V, G dash sin V, F dash. R2 vector is equal to minus G sin V, G cos V 0. And dot product between R1 and R2, that is R1 dot R2 is equal to 0. So that the parametric curves are orthogonal. To find the direction of the normal, we find R1 cross R2 is equal to, we find the determinant value, that is I vector into minus G into F dash of cos V minus J vector into F dash G into sin V plus G into F dash. And the modulus value of R1 cross R2 is G squared into F squared plus G squared. Now n vector, capital N is equal to, normal vector is R1 cross R2 by H is equal to the value of R1 cross R2 I into minus G F dash cos V minus J into F dash G sin V plus G into F dash divided by H value is modulus value F squared plus G dash squared. Next the form definition, anchor ring. The anchor ring is a surface generated by the rotating circle of radius A about a line in its plane at A, distance B greater than A from its center. This circle does not meet the axis of rotation, whereas in the case of sphere, the curve is a semicircle meeting the axis of rotation at 2 points. Next theorem statement, the position vector of a point on the anchor ring is R vector is equal to B plus A cos u into cos V, B plus A cos V into sin V, A sin u. First one is R1, R2, R3. R vector is equal to x, y, z. X coordinate, y coordinate and z coordinate. X coordinate is B plus A cos u into cos V. Y coordinate is B plus A cos u into sin V. And z coordinate is A sin u, where B0, 0 is the center of the circle and z axis is the axis of rotation. Proof of the theorem. Taking the axis revolution as the z axis and the generating circle in the xyz plane with the center C on the x axis, we shall first find the coordinates of the points A on the circle. Let CA make an angle U with the axis. The x coordinate of alpha is A sin u, hence A has the coordinates. Let P of xyz be the position vector of a point A after the generating circle has revolved through an angle V, since the point A describes a circle about the z-axis. Distance at P from the z-axis is the radius of the circle given by B plus A cos u. Since it has been revolved through an angle V, the x and y coordinates are B plus A cos u into cos V, that is the x coordinate, and y coordinate is B plus A cos u into sin V. For the point A as well as the point P, its z coordinate A sin u is always constant. Hence the position vector of the point P on the anchor ring is given by R vector is equal to B plus A cos u into cos V, V plus A cos u into sin V, A sin u, where u lies between the value 0 and 2 pi, V lies between 0 and 2 pi, where u is equal to constant. CA is fixed and revolves about the z-axis. Hence it is a circle on the anchor ring and these curves are parallels. When V is equal to constant, the rotating plane is fixed. Hence the parametric curve for u values lies between 0 and 2 pi is the intersection or the cross section of this plane and the anchor ring, so that it is generating circle. Thus the meridians are circles. Further, R1 vector is minus A sin u cos v minus A sin u sin v, comma A cos u, that is x, y and z coordinates. And R2 vector is equal to minus B plus A cos u into sin v, that is x coordinate, and y coordinate is B plus A cos u into cos v, and z coordinate is 0. Since R1 dot R2, we take the dot product between R1 and R2, that is equal to 0. The parametric curves are orthogonal. The dot product of R1 and R2 is 0, that is the parametric curves are orthogonal. Next, R1 cross R2, the cross product between R1 and R2 is, we are taking the determinant value and expand the value, we get minus B plus A cos u into A cos u cos v, comma A cos u sin v, that is y coordinate, comma A sin u, that is the z coordinate. Since b greater than a, the above vector is negative for the range of values of u and v, so that the normal is directed inside the anchor ring, that is the modulus of the R1 cross R2 value is always positive. Next, let us go for one definition. Already you know the definition, I think. Helicoids definition: the surface which are generated not only by the rotation along, but by the rotation followed by the translation. Such a motion is called a screw motion. The surface generated by the screw motion of the x-axis is called a right helicoid. Representation of a right helicoid. This is the helicoid generated by the straight line which meets the axis at right angles. Okay. If we take the x-axis as the generating line, it rotates about the z-axis and moves upwards. Let OP translated position of the x-axis after rotating through as angle V. Let XYZ be the coordinates of P. Draw a PM is perpendicular to the XOY plane, and let OM is equal to U, then X equal to U cos V, Y is equal to U sin V, and Z equal to PM. By assumption that distance PM is equal to Z, translated by the axis, is proportional to the angle of rotation, taking the constant of proportionality to be, let Z by V is equal to A. Hence, the vector of any point on the right helicoid is R vector is equal to U cos V, U sin V, AB. Now, R1 vector is equal to, that is differentiate with respect to U. R vector, differentiate R vector with respect to U, you know well. That is R1 is equal to cos V, sin V, comma, there is no U in the Z coordinate plane. So, that is 0. And R2 means differentiate R with respect to V. So, that is minus U sin V, U cos V, there is a V in Z coordinate, so A. Since R1 dot R2 is equal to 0, we are taking the dot product between R1 and R2, we get the value 0, that is cos V into minus U sin V plus sin V into cos V plus 0 into A. That is R1 dot R2 is 0, the parametric curves are orthogonal. The value is 0, that means the curves are orthogonal. When U is equal to constant, then the equation of the helicoid becomes R is equal to U cos V, U sin V, AB, which are circular helicoids on the surface. The parametric curves V is equal to constant are the generator at the constant distance from the XOY plane. Further, the cross product, already we are taking a dot product R1 dot R2, that is the surface are orthogonal, and we are taking cross product between R1 and R2. So, that is the value is A sin V, comma A cos V, comma U. We are taking the determinant value of R1 cross R2, expand the value, and we get this value. And H is equal to root of square root of A squared plus U squared. H means R1 cross R2, already you know the formula. H means square root of modulus of the value R1 cross R2. Hence, the unit normal n is equal to R1 cross R2 divided by modulus of R1 cross R2. So, the value A sin V, comma A minus A cos V, comma U, that is R1 cross R2 divided by H. H means root of A squared plus U squared. Next definition, pitch of the helicoid. If V is equal to 2 pi, then 2 pi A is the distance translated after complete rotation. This is called the pitch of the helicoid. Next, representation of the general helicoid. in general helicoid with the z-axis, as the axis is generated by the curve of intersection of the surface with any plane containing z-axis, since the section of the surface by such planes are congruent curves. Without the loss of generality, we can take the plane to be XYZ plane and generates a helicoid. Thus, the equation of the generating curve in the XYZ plane can be taken as x is equal to g of 0, y is equal to 0 and z equal to f of u. Let the curve in the XYZ plane rotate about the z-axis through an angle v and let it have the translation proportional to angle v of rotation, which we can take it as a v. Since any point of the generating curve traces a circle with the center on the z-axis and radius g of u, and z coordinates translated through AV, the position vector of any point R on the general helicoid is R is equal to g of u into cos v, g of u into sin v, comma f of u plus AV. These are all the x, y, z coordinates. R1 vector, differentiate R with respect to u, the value of R1 is g dash of u into cos v, g dash of u into sin v, last z coordinate f of u, differentiate with u, we get f dash of u. Next, R2 vector, R2 means differentiate R with respect to v, that is the value, answer is minus g of u sin v, g of u cos v, comma a, z coordinate value. We are taking the dot product between R1 and R2, we get the value f dash of u into a. When the parametric curves are orthogonal, then either f dash of u is equal to 0 or a is equal to 0. If f dash of u is equal to 0, f of u is constant, you know well this value. The derivative is 0, that is the variable f function is a constant. So that the surface is a right helicoid. If a is equal to 0, we do not have a screw motion and we have only rotation about z-axis, so that the helicoid is a surface of revolution. When v is equal to constant, the parametric curves are the various position of the generating curve on the plane of rotation. When u is equal to constant, it follows from the equation of the helicoid the parametric curves on the surface. Next, the metric on a surface, the first fundamental form. Let r vector is equal to r vector of uv be the given surface. Let the parameters uv be the functions of single parameter t. Then r vector is equal to r vector of u of t, v of t is a function of a single variable t, and hence it represents a curve on the surface with t as a parameter. The arc length in terms of a parameter is given by ds by dt whole square is equal to dr by dt into dr by dt is equal to dr by dt whole square. Dr by dt is equal to dou r by dou u into dou u by dou t plus dou r by dou v into dou v by dou t. Substitute 2 in 1. ds by dt whole square is equal to r1 into r2 of ds by dt whole square plus 2 r1 into r2 ds by dt into dy by dt plus r1 dot r2 into dy by dt whole square. That is the third equation. Let E is equal to r1 dot r1, f equal to r1 dot r2 and g equal to r2 dot r2. Using the notation third can be rewritten in terms of differentials ds squared equal to E du squared plus 2 du dv plus g dv squared. First definition, the first fundamental form are the metric on the surface. The two differential quadratic form ds squared equal to E du squared plus 2f du dv plus g dv squared is called the first fundamental form or metric on the surface. It is usually denoted by I. First theorem, the first fundamental form of the surface is positive definite quadratic form in du by dv. Proof, a quadratic form q is equal to a11 x1 square plus a12 x1 x2 plus a22 x2 square. This is a quadratic form for real values of x1 x2 is called positive definite. If q greater than 0, for every x1 x2 is not equal to 0, 0. The conditions for q to be positive definite are a12 is equal to a21, a11 greater than 0 and a11 a22 minus a1 squared greater than 0. We shall verify that I is equal to E du squared plus 2f du dv plus g dv squared satisfies the above conditions for the positive definite quadratic form. Since we are concerned only with the ordinary point, R1 cross R2 is not equal to 0 and H squared equal to, H means R1 cross R2 and H squared equal to modulus of R1 cross R2 greater than 0. H squared is equal to modulus of R1 cross R2 whole squared. That is R1 squared into R2 squared minus modulus of R1 into R2 whole squared. That is H squared equal to, can be rewritten as Eg minus F squared. Since H greater than 0 always, Eg minus F squared always positive. And also we have the, from the definition, E is equal to R1 dot R1 is equal to R1 squared positive and G is equal to R2 dot R2, that is R2 squared is always positive. Hence 2 satisfies the condition 4 for a positive quadratic form. So as we have E du squared plus 2f du dv plus G dv squared is greater than 0 for all values of u comma v not equal to 0 comma 0. The theorem, the metric is invariant under a parametric transformation. Proof of the theorem, let the parametric transformation be u dash is equal to phi of uv, v dash is equal to xi of uv. In the parametric system, u dash v dash, let the equation of surface r vector equal to r vector of u dash comma v dash. R1 dash is equal to dou r by dou u dash, r1 into dou u by dou u dash plus r2 into dou v by dou u dash. R2 dash is equal to dou r by dou v dash, r1 vector into dou u by dou v dash plus r2 into dou v by dou v dash. Du is equal to dou u by dou u dash into du dash plus dou u by dou v dash into du dash. That is dv is equal to, these are you know well about these values. dv is equal to dou v by dou u dash into du dash, dou v by dou v dash into dv dash. If E dash, F dash and G dash are the first fundamental coefficients in the new parametric system, then we have E dash into du dash squared plus 2f dash du dash dv dash plus G dash dv dash squared is equal to r dash du dash plus r2 dash dv dash whole squared. Using 1, 2, 3, 4. In equation 5 we obtain E dash du dash squared plus 2f dash, that is the fifth equation, is equal to E into du squared plus 2f du dv plus G dv squared. Another problem here, explain. Find E of G and H. Find the values of E, F, G and H for the paraboloid x equal to u, y is equal to v and z is equal to u squared minus v squared. Listen, any point on the paraboloid has quotient vector. R vector, you know well, R vector is equal to what? X comma y comma z. So here also x value is u and y value is v and z value is u squared minus v squared. And now differentiate R vector with respect to u. What's the value? R1 vector is equal to R1 dash 1 comma 0 minus 2u. And R2 is R vector, differentiate R vector with respect to v. So 0, 1 minus 2v. We know the value, what's the value for E? R1 dot R1, R1 squared, that is 1 plus 4u squared. What's the value for F? R1 dot R2, so 4 into uv. And value for G is R2 dot R2, that is R2 squared. So that is 1 plus h squared, that is Eg minus F squared. The value for Eg 1 plus 4u squared into G, E value 1 plus 4u squared, G value is 1 plus 4v squared minus F squared value is minus of 4uv whole squared. So answer, the value for h squared is 1 plus 4u squared 4v squared. We are taking the square root, that is h is equal to root of 1 plus 4u squared plus 4v squared. Thank you.